I will review Kermit Brown's composite IPR model. The standard Vogel equation is designed strictly for solution gas-dried reservoirs with no water production. However, mature reservoirs produce oil and water simultaneously. Brown resolved this challenge by creating a composite model that dynamically merged both fluid behaviors based on water cut. Water inflow behaves linearly following Darcy's law, while oil inflow behaves parabolically below bubble point at Vogel's curve. Let's look at these opposing fluid behaviors. Below bubble point, oil releases gas, which increases flow resistance and creates Vogel parabolic curve. Water, however, it does not release gas. It remains strictly linear, following Darcy's law across the entire pressure range. Brown divides the composite curve into three distinct flow regions. First is the monophasic zone above bubble point, where flow is purely linear. Second is the composite zone, the biphasic core that dynamically combines Darcy water flow and Vogel oil behavior. Third is the limit zone at extreme drawdown, where Vogel becomes unstable and requires a straight-line tangent extrapolation to 0 psi. In the first interval, the flowing bottom hole pressure remains above the bubble point pressure because no free gas is liberated within the reservoir matrix. The global productivity index remains completely constant. This yields a predictable straight-line performance curve dictated by Darcy's linear law. Interval 2 represents simultaneous multiphase flow below bubble point. Free gas restricts oil mobility, creating Vogel's quadratic curve, while water continues flowing linearly. To solve the linear parabola or straight intersection analytically, Brown introduced four coefficients. Coefficient A normalized flowing pressure relative to bubble point and water cut. B weighs water cut flow resistance under biphasic conditions, and finally C and D represents the linear in constant terms of the resulting quadratic system. This gives us an explicit algebraic solution for the total flow rate in the biphasic zone. The key benefit of this analytical rigor is that it completely eliminates slow numerical interactions. This allows fast optimization loops in commercial nodal analysis software. Interval 3 covers extreme drawdowns at very low pressure. Here, Vogel equation can produce mathematically erratic behavior. Brown resolves this boundary constraint by projecting a straight tangent line from the boundary pressure down to 0 psi, ensuring a realistic absolute open flow potential. In summary, this model provides highly reliable AOF potential for high water cut wells, avoiding overestimation. It adapts dynamically over the well's lifespan as water could increase. Ultimately, it serves as the numerical foundation in software like PipeSync and Prosper to safely size artificial lift systems like ESPs and gas lift strings. Now, let's see this model running in our program. First, we input the reservoir pressures, the productivity index, and the water cut percentage. The software automatically evaluates the operating pressure range and it falls in the biphasic region. The code instantly computes coefficients A, B, C, and D to solve the explicit quadratic equation. For extreme drawdowns, it simply applies the tangent line extrapolation, and finally, the program The program plots the iterative composite IPR curve, displaying the smooth transition from Darcy linear flow to the biphasic curve, allowing for rapid and accurate production optimization.